Alright guys, this is your type of forces notes. Today we're doing two of the pages, the flap that says type of forces, and then the difference between balance, unbalance, and calculating net force. So those are the two we're going to do. First of all, we know that a force is a push. We know that a force is a push or pull that causes something to accelerate. A push or a pull that causes something to accelerate. All right, let's talk about different ways that things can be pushed or pulled, right? So we're going to learn about friction. We're going to learn about weight, which is also called force gravitational. You need to know that. You need to know that. This is also called force gravitational. Weight is also called force, what? Gravitational, F sub G. It's very important. This is going to be the exam question for sure. I might ask you, what's the other name for weight? Or if I say, calculate the force gravitational, you're really calculating the weight. And you're also going to learn about this other weird force. It's not that weird because it's normal force. We're going to learn about air resistance or force air drag and also force tension, right? These are the really kind of straightforward forces that we deal with in our everyday lives, but of course there's also the electrical force, the electromagnetic forces as well. All right, so let's start with friction. So you can get pushed or pulled by friction, right? A friction force is a force that opposes or slows down motion. This is caused by physical contact between surfaces. So this is a contact force, right? It's contact force, right? As opposed to a field force like gravity. Okay? The amount of friction depends on the texture of the surface or the type of surface. The texture, you can just put texture. A rougher surface is going to cause more friction than a smoother surface, right? Let's see. When you have experience with this, like if you rub your hands together real quick, like rub them together, or you know run on pavement, you feel the bottom of your shoes, and you notice that the motion that you were hitting the ground with wasn't 100% put into the ground, but it also changes some of your motion into heat energy, right? Like a match on a lighting a matchstick, like right. Okay, next let's talk about weight. Okay, any two masses, this is important. If you have mass, you have force gravitational. Okay, so link these together, link these two concepts together. You have mass, you have weight. Now, mass and weight are different from each other, right? This is an attractive force that depends on the mass of two objects as well as the distance or the radius between them, right? All right, now, actually weight and force gravitational is the weakest force in the entire universe. But we feel Earth's gravity because the Earth is so massive. In fact, it's like 6.46 times 10 to the 26 kilograms. It's really, really huge, right? Because here is the equation for force gravitational. The actual long equation is the gravitational constant times the mass of the object 1 times mass of object 2 over the distance between them squared, right? So if you change the distance between the two objects, the force is going to either increase or decrease, right? So if I increase how far it is, the force gravitational is going to go way, way down, okay? All right, now, let's see. Normal force. This one's kind of cool. This force is the result of two surfaces, or any surfaces, um, so surfaces that push against each other. So pushing against each other, okay? Two forces pushing against each other. And I have an example here. This is kind of a rudimentary example, but the one that I usually like to do, go ahead and turn this into a table. So this book is sitting on a table here, right? So force gravitational, or weight, is going to pull it downward, right? And what causes the book to remain motionless, or velocity 0, no acceleration, right? No acceleration, so no change in velocity, and I have 0 acceleration. What's going to balance this interaction out is the fact that the table is pushing up at a right angle, right? So that's why it's normal. The word normal actually just means 90 degrees. Okay, so look at this vector here. It's actually 90 degrees to the surface, and this is the normal force, right? Now, if I have the wall, so this is a wall here, and I have a red guy here, or gal, pushing against the wall. Normal force isn't always just up. Okay, you're pushing into the wall. This is your force applied. The wall is going to push back on you. The wall is going to push back on you at a 90-degree angle. And this would be force normal now. Okay. So force normal just means 90 degrees to the surface. Okay. So if I push into the wall, the normal force is going to push back. Okay, let's go down to air resistance. Air resistance is a force that opposes force gravitational when you're falling. Okay, it opposes force gravitational. What's the other word for force gravitational? That's weight, right? It opposes force gravitational while falling, or when falling. It is the friction of air against an object. The amount of air resistance depends on a couple things. It depends, obviously, on how fast you're going, because the faster you go, the more the air is going to drag against you. The shape of the object, right? If you try to drop like a feather or bowling ball, it's going to be very different, right? It's going to slow down a little bit different. And also the size of the object. All right. So really, really important here is the force pulling down when you jump out of an airplane is force gravitational or weight. And you have a little bit of air drag. So this is force drag. I'm going to put a D for drag. Or you can even do that for wind resistance. Right, there's another way. And it's gonna make it so that when you have this situation right here, this is not free fall. Okay? As we know, the definition of free fall is only when force gravitational is acting on you. Okay? Let's look at tension. Tension is a force that's transmitted through a rope, a cord, or a wire. Okay? When it's pulled tight by forces acting from opposite ends. The tension force is directed along the length of the wire and is constant or the same on both ends of the wire. So right here, this guy might be pulling back with, he might be pulling back with 10, and what's the unit for force? First an N, right? It's like Isaac Newton, right? And this guy might be pulling back with 10 newtons of force as well. Who feels more force? Well, if there is no acceleration, that means the force net is 0, right? None of these guys are accelerating, so guess what? They have to experience the same amount of force. So this point of the line would have 10 newtons and 10 newtons going each way. This part of the wire would also have 10 newtons and 10 newtons pointing each direction. Every point of the wire is going to have the same force applied to it. All right, let's go ahead and move on to the next part. Let's look at the difference between balance, unbalance, and net force. All right, balance forces are equal. It's the equal sign right there, right? In size and opposite in direction, okay? They, if you are not moving, so if you already weren't moving, if you're just sitting still like this picture here, if I have a net force balanced out on both sides, so my downward force of force gravitational here would be, let's say this is 640 newtons. The table is going to push back up with 640 newtons. I would not move, right? I would not be moving, right? But now if I had horizontal axis, if I had 10 newtons applied and 10 newtons back, I also would have no change in motion, right? So as long as you're not moving, this will not result in motion. But this, better yet, it's not going to have a change in velocity, right? That's important. All right, so right now the net force is 0 newtons because I'm not moving and I'm applying a force up and down and it ends up balancing out. All right. Unbalanced forces are different in size and opposite in direction. So they're different in size and opposite in direction. If the forces on an object are unbalanced, a change in motion will result. A change in motion or acceleration, right? Acceleration will result. Okay? So let's look at the example here. So pulling on the rope, you can tell that there's motion this way, right? If there was equal forces, if the forces were balanced out completely, it would look something like this, right? There's some arrow going this way, arrow going that way. You would have no change in motion. But it's obvious here that there is actually a greater force being applied on the left side because it looks like they're accelerating that way, right? They were motionless and now they're starting to move. In order to start to move, don't you have to speed up? Yeah, so right there, you have acceleration to the left. Or you can say negative direction, right? Negative acceleration to the left. All right. Now let's look over at the last picture we have here. We got to wrap this up, right? All right. The net force is the sum, and that symbol is this, the sigma forces, right? You can just use sum. You don't have to worry about this one until physics. All right. Sum of all forces acting on the object. Now, if I have somebody pushing a box and then somebody comes up behind me and pushes in the same direction, guess what? You add up those vectors, right? It's plus. Now, if they're opposite, remember in mathematics, the opposite of a plus sign is a negative. The opposite of negative is positive. So if they're going opposite, you have to subtract them from one another, right, to get the net force. So here's an example here. If I'm pushing into the box with 10 newtons and somebody else is pushing into the box with 10 newtons, well, this would go like this, right? So force net is force 1 plus force 2. Okay, keeping in mind that we're going to say to the right is positive, to the left is negative. So let's put these in. Negative 10, right? This negative 10 right here, plus 10 gets you 0 newtons, right? 0 newtons. So I'd have no change in motion here. But let's look at one more example. Right? If I have a box, all right, if I have a box here, and I do this, right? So this vector is a little bit larger. Let's assign some values to it. 10 newtons to the right, 2 newtons to the left. Well, what's my net force going to be? Negative 2 newtons plus 10 newtons, and I get positive 8 newtons to the right. Okay? So you have to make sure you have a direction force as a vector quantity. All right, and just to make things a little bit silly, take a look at this guy right here. I want to see if you can figure out what this would be. All right, see if you can figure out what this would be. Okay. Let me straighten out this vector. Huh. Okay, I'm going to assign some values here. Let me see if you're savvy. 3 newtons, 4 newtons. What's going to be the result of this? Well, you kind of remember from when we were doing displacement that the result is going to be to the right and down, right? To the right and down. And guess what this is? This is a triangle, right? Remember this triangle? 3, 4, if you do Pythagorean theorem, 3 squared plus 4 squared equals c squared. Square root that on both sides. You end up getting, guess what? 5 newtons down and right. Cool or what? All right. Good luck.